In the next several minutes, you will discover why astronomers are tracking an object that survived a 7 billion year journey through deep space, why it is spraying interstellar material into our solar system right now, and what scientific discoveries await when it reaches closest approach in exactly 32 days. Imagine an object smaller than 1 kilometer across. This object traveled through the Milky Way for billions of years. It passed through regions of space where energy levels barely register. Then, on October 29th, 2025, everything changed. The object screamed past our sun at 68 kilometers per second. That makes it the fastest observed object in astronomical history. Now, it is actively ejecting ancient interstellar material directly into our solar neighborhood. On December 19th, 2025, this visitor will make its closest approach to Earth. This is 3I Atlas, the third confirmed interstellar object ever detected, and right now it is giving scientists a once-in-a-lifetime opportunity to study matter that formed in a completely different part of our galaxy. The story begins not with its arrival, but with its origin. Every object tells a story through its chemistry. Every trajectory reveals a history. And 3I, Atlas carries secrets from a region of space our species has never directly sampled. Astronomers estimate this comet spent approximately 7 billion years traveling through the galactic disk. Not the thin disk where our sun orbits, not even the outer halo. This object likely originated from what scientists call the thick disk of the Milky Way. That region contains some of the oldest stellar populations in our galaxy. Stars there formed when the universe was younger, when heavy elements were scarcer, when planetary systems looked fundamentally different from what we see today. The chemistry of 3I Atlas reflects this ancient heritage. Spectroscopic analysis shows compounds that suggest formation in a low metallicity environment. That means less iron, less silicon, fewer heavy elements compared to objects born in our local stellar neighborhood. This comet, assembled from materials that condensed around stars born billions of years before our sun even existed. Think about what that means. The ice and rock that make up 3I Atlas formed in orbit around a star we will never identify. A star that may no longer exist. That parent system could have had planets, maybe even conditions suitable for some form of chemistry we would find interesting. But gravitational interactions ejected this small body. Perhaps a passing star disturbed the system. Perhaps a giant planet migrated inward and scattered smaller objects. We will never know the exact mechanism. What we do know is that 3I Atlas was flung into interstellar space millions or even billions of years ago. For most of that journey, this object experienced conditions almost impossible to describe. In interstellar space, temperatures hover just a few degrees above absolute zero. Radiation levels are incredibly low. Energy flux measures somewhere around 10 to the power of -7 watts per square meter. Some estimates go even lower, down to 10 to the power of -8. At those energy levels, chemical reactions essentially stop. Ice remains frozen in configurations that never change. Cosmic rays slowly alter surface chemistry, building up organic compounds grain by grain. This process created a thick, insulating crust, a protective layer that locked the pristine interior away from any external influence for geological timescales. Then 3I Atlas entered our solar system, and everything changed. The object approached at a velocity that immediately identified it as interstellar. When it first crossed into the detectable range, measurements showed 58 kilometers per second relative to the Sunday. That speed exceeds the escape velocity of our solar system by a significant margin. No object bound to our sun could naturally achieve that velocity at such distances. This was clearly a visitor from beyond. As 3I Atlas plunged deeper into the inner solar system, the sun's gravity accelerated it further. By the time it reached perihelion on October 29th, Velocity had increased to 68 kilometers per second. To put that in perspective, most comets from our own Oort Cloud reach perihelion at speeds between 40 and 50 kilometers per second. Even the fastest long-period comets rarely exceed 60. This interstellar visitor was moving faster than anything astronomers had tracked before. That speed creates unique observational challenges. The object crosses huge angular distances in very short time frames. Tracking requires precise ephemeris calculations. Any error in predicted position makes follow-up observations difficult or impossible. Early trajectory estimates contained significant uncertainties. Scientists knew the general path, but exact predictions for future positions had error bars measured in arc minutes. For professional observatories, that level of uncertainty is manageable. For coordination between multiple facilities, it becomes problematic. Then something unexpected happened. A spacecraft, orbiting a completely different planet, captured images that changed everything. The ESA ExoMars Trace Gas Orbiter is a scientific mission studying the Martian atmosphere. Its primary objectives involve detecting trace gases and mapping surface composition. The spacecraft carries a camera system called CASIS, designed for high-resolution imaging of Mars. But in early October 2025, mission controllers pointed that camera away from Mars and toward a fast-moving dot in space. 3. I-Atlas was passing relatively close to Mars during its inbound trajectory, close enough that the Trace Gas Orbiter could acquire images from a completely different vantage point than Earth-based telescopes. This created a parallax measurement of extraordinary precision. Parallax is the apparent shift in position of an object when viewed from two different locations. The farther apart those locations, the more accurate the distance measurement. Earth and Mars were separated by over 100 million kilometers at that time. That baseline allowed astronomers to triangulate the exact position of 3I Atlas with unprecedented accuracy. The data from Mars improved orbital trajectory calculations by a factor of 10. Suddenly, predictions about where the comet would be weeks or months into the future became vastly more reliable. Error bars shrank from arc minutes to arc seconds. This level of precision proved critical for planning future observations. It also definitively ruled out certain exotic possibilities that had been circulating in scientific discussions and public speculation. Some researchers had proposed that 3I Atlas might exhibit significant non-gravitational acceleration. Non-gravitational forces are common in comets. As ice sublimates, it creates jets of gas that act like tiny rocket engines. These jets can slightly alter a comet's trajectory. For most comets, this effect is small but measurable. Some speculation suggested that 3I Atlas might show unusually large non-gravitational acceleration. Perhaps its interstellar origin meant unusual chemistry. Perhaps the thick organic crust would sublimate differently than normal cometary ice. Perhaps something more exotic was occurring. The Mars data answered these questions definitively. 3. I-Atlas is experiencing minimal non-gravitational acceleration. The measured effect falls well within the normal range for cometary outgassing. There are no anomalies, no unexpected trajectory changes. The object is behaving exactly as a comet should behave when warmed by solar radiation. But while its trajectory proved ordinary, its appearance became anything but. As 3I Atlas approached perihelion, something remarkable began to happen. The sun's energy started penetrating that ancient insulating crust. Remember, this object spent billions of years in an environment where energy flux measured around 10 to the power of -7 or -8 watts per square meter. At perihelion, energy flux increased to 735 watts per square meter. That represents an increase of 10 to 11 orders of magnitude. It is difficult to find analogies for that kind of energy jump. Imagine going from the faintest starlight to standing next to an industrial furnace. That barely captures the scale. The pristine ice locked beneath the organic crust began to sublimate violently. Gas erupted from multiple locations across the nucleus. Dust entrained in that gas created a visible coma that expanded rapidly. Within days, 3I Atlas went from an inactive point of light to an active comet, displaying multiple tails and jets. But here is where things get scientifically fascinating. Most comets develop tails that point away from the Sunday solar wind, and radiation pressure push gas and dust outward, creating the familiar teardrop shape. 3I Atlas developed that. But it also developed something extremely rare, a jet pointing directly toward the Sunday. Sunward-pointing jets are extraordinarily uncommon. Astronomers can count on one hand the number of comets observed to display this feature with confidence. The phenomenon requires very specific conditions. A localized area of intense sublimation must occur on the sunward-facing hemisphere. The gas pressure must be strong enough to overcome the outward push of solar radiation. And the observation geometry must allow us to actually see the jet against the bright background of the inner coma. 3I Atlas displayed this feature clearly in images taken during the second week of November. By that time, the comet had already passed perihelion and was moving back out toward the outer solar system. Yet activity remained high. Multiple jets could be seen extending from the nucleus in different directions. The sunward jet appeared as a distinct linear feature cutting through the coma toward the Sunday. Other jets extended sideways and backward, creating a complex fountain-like structure. The tail structure also showed unusual complexity. Most comets display two tails: a gas tail composed of ionized molecules that glows faintly and points directly away from the Sunday, and a dust tail composed of solid particles that curves gently as particles follow slightly different orbits. 3I Atlas showed both. But careful examination of images revealed additional structures. Streamers of material extended at odd angles. Knots and condensations appeared in the tail, suggesting episodic bursts of activity rather than steady sublimation. This complexity tells scientists something important. The nucleus is not uniform. Different regions have different compositions or different thicknesses of insulating crust. As the comet rotates, different areas become illuminated by sunlight. Each area responds differently. Some regions erupt violently. Others remain dormant. The resulting activity creates a time-variable display that changes from day to day. On November 16, 2025, a new image captured from New Mexico showed 3I Atlas in unprecedented detail. This was not a spacecraft image. This was a ground-based observation using equipment available to dedicated amateur astronomers. The exposure revealed fine structure in the coma and tails that had not been visible in earlier images. Multiple jet features could be traced back toward the central nucleus. The dust tail showed clear stratification, with distinct lanes of material separated by darker gaps. Thank you for being with us. Please subscribe, share, and like. This level of detail allows scientists to model the nucleus structure. By tracking how jets evolve over time, researchers can infer the rotation rate. By measuring the brightness and color of different tail features, they can estimate particle sizes and compositions. Each new image adds data points to models that are attempting to reconstruct the internal structure of an object we can never directly sample. And that gets to the core scientific value of 3I Atlas. This comet is not just a curiosity, it is a geological sample from a completely different part of the galaxy. Everything it contains formed somewhere else, under different conditions, from a different mix of starting materials. By studying this object, scientists are essentially conducting remote geology on a planetary system we will never visit. The material being ejected right now is spreading through the inner solar system. Dust particles are being blown outward by solar radiation pressure. Some of that dust will eventually intersect Earth's orbit. In a year or 2 or 3, Earth may pass through debris trails left by 3I Atlas. When that happens, We might see meteor showers composed of interstellar particles, tiny grains of matter from another star system burning up in our atmosphere. Scientists are already calculating when and where those intersections might occur. The gas being released also has scientific value. Spectroscopic observations can identify individual molecules: water, carbon monoxide, carbon dioxide, methane, ammonia, and dozens of more complex organic compounds have been detected in the coma. The ratios between these molecules provide clues about formation temperature and radiation environment. Some molecules indicate formation in very cold conditions. Others suggest processing by cosmic rays or ultraviolet radiation over millions of years. One particularly interesting detection involves complex organic molecules, long-chain carbon compounds that require specific formation pathways. These organics likely formed in the insulating crust during the long interstellar journey. Cosmic rays, striking ice and simple carbon compounds, can build up more complex structures through radiolysis. Over millions of years, this process can create a rich organic chemistry. Some of those molecules are now being liberated as the comet warms. Scientists are cataloging them, comparing them to organics found in solar system comets, looking for differences that might reveal something about interstellar chemistry. 3. I-Atlas will not stay near Earth forever. It is moving on a hyperbolic trajectory. That means it will escape our solar system just as surely as it entered. Right now, the comet is traveling outbound, moving farther from the Sun each day. Activity will gradually decline as energy input decreases. Eventually, sublimation will stop entirely. The coma will dissipate, the tails will fade. 3. I-Atlas will return to the frozen, dormant state it maintained for billions of years. But before it leaves, there will be one more close encounter. On December 19, 2025, 3I-Atlas will make its closest approach to Earth. The exact distance will be far enough to pose no danger whatsoever, but close enough to allow detailed observations from multiple facilities. Space-based telescopes will track it. Ground-based observatories across multiple continents will coordinate observations. Spectroscopic campaigns will run continuously to capture the maximum amount of data during this optimal viewing window. After December, 3I-Atlas will continue outbound. In March 2026, around the 17th, it will pass relatively close to Jupiter. That encounter will provide the final gravitational boost that sends the comet back into interstellar space. Jupiter's massive gravity will accelerate the object, increasing its velocity beyond even the 68 kilometers per second it achieved at Perihelion. By the time 3I-Atlas crosses the outer edge of the solar system, it will be moving faster than when it arrived. Then it will be gone. Billions more years traveling through the void. Perhaps it will eventually encounter another star system. Perhaps it will be captured into orbit around another sun. Perhaps it will wander the galaxy until the stars themselves burn out. We will never know. The scientific community has engaged in vigorous debate about 3I-Atlas since its discovery. Most astronomers agree on the basic facts: interstellar origin, cometary composition, natural object. But some researchers have proposed more exotic explanations. One hypothesis suggests that the observed non-gravitational acceleration, while small, might not be entirely explained by normal outgassing. This hypothesis proposes that some additional mechanism could be contributing to the trajectory. The researcher most prominently associated with this idea has a history of proposing unconventional explanations for interstellar objects. In the case of the first interstellar object, Oumuamua, this researcher suggested possible artificial origins. With 3I-Atlas, similar speculative ideas have been put forward. The suggestion is that the measured acceleration might indicate some form of propulsion. The vast majority of astronomers reject this interpretation. The measured non-gravitational acceleration is entirely consistent with normal cometary outgassing. There is no need to invoke anything beyond well-understood physics. Comets accelerate when gas jets push on them. The measured effect on 3I Atlas falls squarely within the expected range. Multiple independent teams have analyzed the trajectory data. All reach the same conclusion. This is a comet behaving like a comet. Why then does the exotic hypothesis persist? Partly because interstellar objects are inherently exciting. Partly because definitive proof either way is difficult. We cannot land on 3I Atlas. We cannot sample it directly. All conclusions must be drawn from remote observations. That leaves room for alternative interpretations, even when those interpretations require assumptions far beyond what the data actually support. The scientific method handles this through weight of evidence. When one explanation requires only well-established physics and matches all observations, while another explanation requires unknown technology and still matches the observations no better, scientists favor the simpler explanation. This principle, often called Occam's razor, is not a proof, but it is a reliable guide. And in this case, it strongly favors the natural comet explanation. As December 19th approaches, preparations are intensifying. Observatories around the world are allocating telescope time. Space agencies are adjusting schedules for orbital assets. Data pipelines are being set up to handle the expected flood of images and spectra. This is a coordinated international scientific effort focused on extracting maximum value from a fleeting opportunity. After 3I Atlas departs, it may be years or decades before another interstellar object passes close enough to study in detail. Oumuamua in 2017 was the first. 2I Borisov in 2019 was the second. Now 3I Atlas in 2025. 3 objects in 8 years suggests that interstellar visitors may be more common than previously thought. Improved detection capabilities are finding objects that would have gone unnoticed a decade ago. Better computational tools are identifying unusual trajectories faster. As these systems improve, the discovery rate should increase. But each object is unique. Each carries information about a different origin. Each provides a different snapshot of conditions in other parts of the galaxy. 3I Atlas, with its ancient thick disk origin and its spectacular activity, represents a particularly valuable data point. The scientific papers resulting from this apparition will be analyzed for years. Models will be refined. Theories will be tested. New questions will emerge. In exactly 32 days, 3I Atlas will reach its closest point to Earth. The countdown is running. Telescopes are ready. Scientists are prepared. And for a brief moment, humanity will have the chance to study matter from another part of our galaxy up close. An object that traveled for billions of years through the dark. An object that carries secrets from stellar systems we will never visit. An object that is now sharing those secrets as it passes through our small corner of space. This is not science fiction. This is happening right now. Thank you for being with us. Please subscribe, share, and like.